S is the spacing of the stirrups. And in case of shear reinforcement, we use, depending on the number of legs you have, shear area is the total area of all the legs. If you have 2 legs, it will be 2 times the area of bar. That's the shear area, A sub V. Okay, so that's your contribution from shear reinforcement. So what it does, ACI does is, it has divided this into 5 ranges. So if my shear force, factor shear force, is less than phi VC over 2. Does anyone remember what phi is for shear reinforcement or shear design? Based on ACI. Phi is only based on ACI. Strength reduction factor for shear 0.75. Okay, it's less than flexural strength reduction factor for flexural condition. So 0.75. So phi times V sub C over 2. That means the design shear strength of just the concrete over 2 will give you a range up to this point. And if my shear is less than that, I don't need any shear reinforcement, theoretically. If the shear force, factor shear force, is between phi VC over 2, which is the phi VC is design shear contribution from concrete, over 2 and phi VC, then you only provide minimum reinforcement. Minimum reinforcement, there is a maximum spacing limit and a minimum S max based on shear reinforcement, minimum shear reinforcement. That's up to this point here. Beyond that, you design your actual shear reinforcement. When you design your shear reinforcement, depending on how severely your beam is loaded, if it is shear critical, then you use a smaller spacing, S max over 4 and about 300 millimeter. That's the maximum spacing of the stirrups or shear reinforcement. If it is not as severely stressed from a shear point of view, then you have S max is D over 2, effective depth over 2, which is and also there is 24-inch limit, which is 600 millimeter approximately. Okay, and if the total shear is greater than 10 times square root of F prime CBW, then we have to revise the section. I'm sure you have similar requirements in IS 446. Okay. What's the maximum spacing of shear reinforcement in IS 456? How much? 300 millimeter. Yeah, that's what we have here. What about in terms of effective depth? 0.75. So it's slightly larger. That's what I thought. But that's anyway. Here it is 1/4. Yeah, 0.25. Because shear reinforcement will give you ductility in any steel beam. So it's always good to add more shear reinforcement than the design requires. Always very helpful, because the actual probability of failure of a beam, if you design it as an under reinforced beam by bending, is practically 0, because it will keep on deflecting and deflecting and deflecting. Then it can even go into the steel bars can go into strain hardening range, as long as you prevent shear failure. If you prevent shear failure, it will have lots of reserve capacity, and that's the reason in earthquake resistant design you have special provisions for shear reinforcement detail, right? You remember that? That's the reason. Okay. So in summary, I have everything in SI units listed here for you to just get a feel for numbers if you are interested. You don't have to know all this, but it's good to know. So Vs max is phi times 0.83 square root of F prime C BWD. That's the absolute maximum you can allow in your section. If this doesn't work, all that you do is change the dimensions. You have to increase the dimensions. Either increase the depth, increase the width, or increase both. Okay, so that's our maximum limit. So I have slightly enlarged version of the one slide, and this time I have everything in SI units. So these 3 slides with SI units. So in case you want to get a feel for numbers, you want to compare the numbers with your IS 456 design equations, you can do that and see where it stands. And of course, some of these spacing requirements have been changed in last 10-15 years. So those of you who are, I don't know how many of you are able to get into IS 456 committees. It's very hard to get into those big ones. ACI 318, it's impossible to go in the committee. It's like that. But there will be always many subcommittees. So you may try to get onto the subcommittees and try to make influence the design. You have to keep changing this. Unfortunately, IS 456 has not changed in 19 years, so that's not good. Anyway, so we have everything here, more enlarged, that's all. The same thing, I have everything in SI units, so this is 5/6, which is 0.8 something, 83 or something like that. So that is for steel reinforced concrete. Okay, what about shear design for FRP concrete, FRP reinforced concrete beams? I already mentioned this, relatively low modulus. We looked at the numbers. That's a problem. So low transverse shear resistance, obviously, and low dowel action. Okay. Then high tensile strength, but no yield point. So that's another problem. So you want to, when I say it's a problem, what I mean is, if you have a linear stress strain curve and the failure stress, let's say the stress at failure is about 1000. So what we do is, we will never ever design with 1000 MPa limit. We'll always design it maybe like 1/3 or maybe 300 or 400 MPa. So all that high strength, the advantage of the high strength is also lost because of the linear stress strain curve. Okay, so that's what I mean. Again, tomorrow when we are summarizing everything, I'll ask you all these questions. So please be prepared. So not that we are grading, but it keeps you thinking about stuff, which is very good. Particularly, you are all professors, so you have to remember, it's always good to do research. High tensile strength is not really advantageous in shear reinforcement. Bent bars have significantly reduced strength. You already told me how much reduction you will have due to bends. So that's another problem. Now, the approach is exactly the same. Design shear strength for a beam should be greater than equal to the factored load Fx, factored load shear. Okay? Strength reduction factor, same as steel reinforced concrete. So you are using strength reduction factor phi of 0.75, because shear failures are more brittle. So how many of you tested beams in your labs? Quite a few, right? Can you remember your beam failing in shear? Yeah, but like, see, you design your test beam based on what you are expecting the failure mode to be, right? If it is fluxural failure, it fails in a very gentle manner, and it takes time, takes its own time, and at some point you will lose patience. Okay, I'm done. I have to go back and do whatever. So you stop the test and go, right? That's for fluxural failure. It takes a lot of deflection, and then it will fail. Eventually, it will fail. However, for a shear failure, you will see, you just take your eyes away, like don't look at the beam for a couple of seconds, it would have failed. Okay? So shear failure is so brittle, that means so sudden. It won't give you any warning, and therefore shear failures are more catastrophic. And that's the reason we always make sure we are safer in shear by at least a larger margin than we are safer in bending. So strength reduction factor reflects that. In case of beams, it is not so bad. Moment strength is based on phi factor of 0.9, whereas shear strength is based on 0.75. Okay. Now, remember the same 5 columns I had. 5 columns I had for shear design for steel reinforced concrete beams. So in case of FRP reinforced beams, we have same approach. Here V sub C is given as 5 times square root of F, it's in PSI units. So bear with me for 2 minutes. 5 times square root of F prime C times BW. Here the shear area is now based on K sub D, K times D. So by our notation, what is KD? KD is the depth to neutral axis under elastic transformed section property, cracked elastic section 3 times, 3 items. One is cracked, elastic and transformed condition. Cracked, transformed and elastic, 3 things. So your KD is based on that, K, at least KD, K. So here itself, K is generally about 0.118, 0.2, something like that of D. So K is 0.15 or 0.2, let's say even 0.2. So you have 0.2 times D is already 20% of the depth. So you lose some strength there. So you can rearrange these terms and say everything else in steel reinforced concrete is related to 2 square root of F prime C. Therefore, I have a 5 factor here in the denominator. So obviously, we are reducing here by a factor of 5 and here by a factor of 5. So your strength, shear strength of concrete will be 1/25th of shear strength of steel reinforced concrete beam. Almost. It may not be exactly 1/25th, but it will be very, very small. Okay. So in SI units, we have 2. It may not be 20. The factor may be slightly less. 2.5 times 5, 12 times. Okay, 1/10. So 10 to 12% of the steel reinforced concrete. Okay. So it will be the shear contribution from concrete for a steel beam or steel reinforced beam, if it is, let's say, 100 units for FRP reinforced beams, shear contribution from concrete is probably going to be 10 or 12 units. Okay, that's what I mean. Okay, so in SI units, you have 2/5 square root of F prime C. Here F prime C is in MPa units. BW times KD. So we know how to find out the value of K based on the previous expression I have. You can easily, if you have some patience and you don't have anything else to do on a Saturday night and you are bored, derive this equation. You will very quickly you will feel sleepy, so you can sleep. So you have trouble sleeping, do this kind of stuff. So anyway, K is derived as this expression here. Plug in all the numbers and then you get your value of K. K cannot be greater than 1, never ever will be greater than 1. The range, normal range is about 0.18, let's say 0.2 plus or minus 0.03. So it will be close to 0.2 D. So you can calculate your K value, then find out your contribution, shear strength contribution from concrete. For shear contribution from shear reinforcement, you use the same equation as in steel reinforced concrete. Very same, exactly same, except that we use area of shear reinforcement, FRP shear reinforcement. So we add additional subscript F and FFV. That's where we'll come back to this. We'll come back to this in a minute. Here it is FFV, F subscript FV. Okay, very important. It's a big difference. It will make a big difference. And what is F subscript FV? It is equal to 0.004 EF. 0.004 EF is 160 MPa. It doesn't matter how strong your FRP material is, because the concrete will crack under significant deformation. Therefore, we have to limit, in order to reduce cracking or limit cracking, we have to limit our stress to 160 MPa. Here it doesn't say what kind of strength you have in the material, and I come back to the same point. Maybe tomorrow that might be one of our highlights. If you want to sell your product, you better have higher modulus, because see, even here it is modulus dominated. Therefore, larger the modulus, larger the FFV. Okay, and then also you need to consider the bend, strength at the bends. This may not govern your design. In most cases it may not, but this will always govern your design. So when we have discussions with FRP producers, bar producers, I try to highlight this, but they don't want to accept that, even though it is the main problem. If you can increase the modulus, it's always helpful. So based on that, you have, of course, if you have inclined bars, you can use that sine theta, cosine theta combination for your shear reinforcement. And how many of you are using any bent bars? Do you use any bent bars? Nobody uses these days. Nobody, because it costs much more to provide a bent bar, at least where labor is very expensive. It's more expensive to make a bent bar and place it than to use just vertical bars at closer spacing. So I think it is highly unlikely you will use these equations, because many people don't prefer using bent bars. Then you also have minimum shear reinforcement requirement and VF max. So once again, we have those 5 columns. All that you need is the table with 5 columns and with all the equations listed in one location, and then you can design your beam for shear. Okay. So this bend radius for shear reinforcement minimum is 3 times dB. This one here. Okay. So when it says 3 times dB, it refers to the center line. Therefore, the inner diameter is 2.5 times dB, inner radius to the inside surface. The mean or center line dimension, the bend radius is 3 times dB. So in summary, of course, there is one other thing. So you should always have a tail length which is greater than or equal to 12 times dB. Okay. That's in steel reinforcement, this is not 12 dB. You probably know that better. So I won't say that. It's more like 6 times dB. In FRP, you need twice as much. Now, so in summary, once again, we'll summarize the shear strength contribution from the concrete alone. That would be this one. Phi is 0.75. Lambda is for weight of the concrete. For normal weight of concrete, lambda equals 1. For lightweight concrete, lambda equals 0.85. And for all lightweight concrete, when you don't have any coarse aggregate in the lightweight concrete, that's 0.7. So for all practical purposes, we will use normal weight concrete. Therefore, that will be 1. Lambda equals 1. And then I adjusted this factor to match your SI units. So that's in place already. And then K is determined based on this simple expression. So, and then phi VF is based on the equilibrium of force equilibrium, obviously. And then the key thing is this limit here, that's what will limit your shear strength capacity of FRP bars. So when you use this limit of FFV equals 0.004 EF, and that should be less than or equal to FFB, so FFV, V for Victor, and this is B for, yeah. So FFB, so it should be less than FFB. Okay, so FFB is given by this equation, we know that. We have VF max, absolute maximum shear force you can apply to your section, regardless of how much our shear reinforcement you have. This is what it is, 0.66 square root of F prime C. F prime C is in MPa units, BW times D. Okay, so based on this, you can make a table very similar to what we had for steel reinforced concrete. Okay, so we have 5 columns, and then for phi VC over 2 greater than V sub U, no shear reinforcement is needed. Between phi VC over 2 and phi VC, you provide minimum reinforcement. We have SI equivalent here. I have that equation in terms of SI units. And then from phi VC to phi VC plus phi F max over 2, that's the other limit. Up to that point, you have S max equals D over 2 and 24 inches, which is 600 millimeter, regardless of beam depth. And then beyond that, up to V max, VF max, or absolute maximum, you have spacing of D over 4, maximum spacing, and this is 300 millimeter. And you must use this VF equals VU over phi minus VCF as your governing equation. That will give you the spacing. So you get the spacing based on FFV. That's a big limiting factor, FFV. Okay. Now, any questions on this? So, Dr. Das, did we print those shear examples? Okay, sorry. So we have some example for you, numerical example. So you might want to go over that, match with these equations. You will see it should match reasonably well. If any mistakes are in the example, it's probably due to conversion, but generally it will be good. It will be okay. Finally, oh, we're not done yet. We have one more item, which is development length. So that is, we'll do that in a minute. So shrinkage temperature reinforcement, many of you in fact are probably thinking of using it for shrinkage and temperature reinforcement. That's what's otherwise known as distribution steel. Distribution steel is provided normal or perpendicular to the direction of the main steel. Main steel is for flexural requirement. Distribution steel, which is perpendicular to the main steel, is for shrinkage control, temperature movement, and things like that. So you can use FRP reinforcement for shrinkage, and you will be able to get away with very small amounts. There we are not looking at strain limits, strength, nothing. Larger the strength, better, because FFU is in the denominator. So this expression here will give you steel ratio for temperature and shrinkage reinforcement, which is the distribution steel. So that ratio is defined as area of FRP over width of the section. Normally, I don't know, do you work in meters or whatever you are working in, it's okay. In PSI units, we work with feet. So 1 foot width, you get your distribution, amount of distribution reinforcement. So if you are using 1 meter, then use that 1 meter as the width. Effective depth is the, no, in this case, the total depth. H is the governing depth. So rho FTS. So h is the overall height, b is the width, normally maybe 1 meter or 1000 millimeter. This can be millimeter. This is area millimeter square. So that is a dimensionless quantity. That equals 414 is the reference strength, which is for your FE 415. So 414 over FFU. FFU can be in MPa units. EF over, sorry, this one should be, what was that? That should be ES over EF. There is a mistake here. I will correct it later. So that should be ES over EF, and it should not be less than 0.0014. Okay. So that's the. Let me correct it right now. I'm sorry. Give me a minute, please. So that's the correct one. Please, in your handouts, I have EF, but that should be ES. S for steel. That's 200 GPa. So use 200 GPa for ES. That's what it should be. Okay? That's all. So with that, we have finished one section for this session. Any questions? Questions? Yes, please. Can you speak up? Yeah, that is the same principle as steel reinforced sections also. There also you use temperature and shrinkage reinforcement to control cracks. Yes. Yes, that's correct. I agree. Is that your question? Yeah, secondary reinforcement. It is secondary reinforcement. Yeah.
Coefficient of laser expulsion for concrete and FRP are not same.
Right, that's true. I agree. I agree.
So
but not all concrete members are subjected to so much of temperature differential, right? So normally it should be okay. That may be a problem in pavements. Like, I don't know what kind of temperatures do you expect in your pavements? Does anyone remember? How much?
normal atmospheric is varies from maximum maybe 45 degrees or 50 degrees.
Yeah, but the concrete will be hotter than the ambient temperature. At least 10-15 degrees, 10 degrees. So, yeah, I know. But the thermal expansion is not necessarily a problem. Anything else? Do you have any questions? So should I move on to the next item?
Can we use steel reinforcement with this?
Yes, except with carbon fiber. You should always talk to the supplier. Sometimes they know there is a problem, so they put some kind of coatings.
Because in bend we have issues with this FRP, so we can easily bend the steel bar instead of using.
Yeah, you can do that. Yeah, mixed mode, absolutely. You want stirrups in steel, but main reinforcement in FRP. Yeah, that's fine. That works. In fact, all my test specimens I do that way, because it's very hard to get, or you have to special order those ties and tell them. If you make a mistake, like one time Dr. Das was telling, they made a mistake and they lost $50,000. $50,000 is like a month's, 1 year's salary for a normal person. So that's a lot of money. So if we make a mistake in dimensions, you're done, right? So yes, I agree. You can use steel reinforced shear reinforcement in your. But only thing is, I don't know how the equations will work, because FRP will still have very low dowel action. Will have, so there will be, you should be conservative a little bit. That means you should be safer. Try to be